An elastic body is subjected to a tensile stress X in a particular direction and a compressive stress Y in its perpendicular direction. X and Y are unequal in magnitude. It can be X greater than Y or Y greater than X. On the plane of maximum shear stress in the body, there will be these are the options given, and this question is being asked in 1989 GATE paper for 1 mark. Okay, here X and Y are the only normal stresses and there is no shear stress. Then absolutely it becomes X and Y are principal stresses. X and Y, these principal stresses can be easily visualized using Mohr circle. Always in Mohr circle, the center of a Mohr circle lies on the X-axis. It never comes on Y-axis. Here I have assumed tensile stress greater than compressive stress. So A, which is X, is greater, and so the center gets shifted towards the right, and B corresponds to Y, which is the minimum compressive stress. Minimum maximum depends on the distance from the origin. From the origin it is Y very small and A it is very big. Here I have given us A as sigma 1, which is the major principal stress, and B is the minor principal stress, sigma 2. Okay, D corresponds to the shear stress, which has only maximum value at D point and diametrically opposite point. These 2 points will be having the maximum shear stress. Other points will be having minimum shear stress. So this DC line corresponds to the plane of maximum shear stress. Always a line which passes through the center of a Mohr circle constitute a plane at that particular point. Here DC is the plane of maximum shear stress. Here you can see that C has a small value of tensile stress from the origin. From the origin you have to calculate. It is a small normal stress whose value is equal to sigma 1 plus sigma 2 by 2. This is a general formula for calculating the center point of a Mohr circle. Sigma 1 plus sigma 2 by 2. And the shear stress, maximum shear stress is sigma 1 minus sigma 2 by 2, which I have mentioned here. T is equal to tau max. So both shear stress and normal stresses are acting. Generally, when X and Y are unequal magnitude on the plane of maximum shear stress, we will be having both normal stress and shear stress. If the two principal strains at a point are 1000 into 10 power minus 6 and minus 600 into 10 power minus 6, then the maximum shear strain is generally strains don't have any dimension. So the maximum shear strains, they have asked the maximum shear strain by giving the principal strains. We know the way to calculate maximum shear stress from the principal stresses, which is tau max is equal to sigma 1 minus sigma 2 by 2. Major principal stress minus minor principal stress divided by 2 gives the maximum shear stress. From the Mohr circle concept, as we have seen earlier, it is the following replacement is being derived, that instead of tau, if we use gamma by 2, and instead of sigma, that is principal stress, we use epsilon, principal strain, we will be getting a relation for the principal strain and maximum shear strain, which comes out to be instead of tau, gamma max by 2, and instead of sigma 1, it is epsilon 1, and sigma 2, epsilon 2. So 2 gets cancelled, and the maximum shear strain is equal to epsilon 1 major principal strain minus epsilon 2 minor principal strain. Here the major principal strain is 1000 into 10 power minus 6, and the minor one is minus 600 into 10 power minus 6. How I derive at major and minor? Major is the value which has higher magnitude, and a minor is the one which has lower magnitude. So 1000 minus 600 will give 1600. So C is the answer. A shaft subjected to torsion experiences a pure shear stress tau on the surface. That is pure torsion concept. The maximum principal stress on the surface, which is at 45 degree to the axis, will have a value. As we have seen earlier, that in the case of pure torsion, always principal stresses both will have the same magnitude, that is tau, but opposite in direction. That is sigma 1 will be tensile and sigma 2 will be compressive. Sigma 1 will be acting at 45 degree to the axis and sigma 2 will be acting at 135 degree to the axis. So they have asked the maximum principal stress, that is major principal stress on the surface, which is at 45 degree to the axis. So they are asking for sigma 1, which comes out to be tau. Even if they ask minor principal stress, we will be saying tau only, but of negative sign. Okay, here comes the tricky part. They have played with the trigonometric knowledge. That is, we know that sine 45 and cos 45 are 1 by root 2. If we just substitute here, we will be getting 1 by 2, 2 gets cancelled, and tau comes out to be the answer. So tau is the actual answer, but they have twisted with this trigonometry concept. So D is the answer. Okay. If the principal stresses in a plane stress problem are sigma 1 100 megapascal, sigma 2 40 megapascal, and the magnitude of the maximum shear stress will be, they have asked just the magnitude of the maximum shear stress. Okay, here we will be seeing the different maximum shear stresses. Before, these are the options, and this question is being asked in 2009 for 1 mark. Okay, what is, if they have asked just maximum shear stress, it is enough to calculate major principal stress minus minor principal stress divided by 2. But if they have asked absolute maximum shear stress or tau max, that is maximum shear stress at a point given, or if they have asked the maximum shear stress in the whole component, then the way of calculating is sigma 1 and sigma 2. Here we have two conditions, that if sigma 1 and sigma 2, that is the principal stresses are unlike, that is both tensile and compressive, in such a case the same formula for maximum shear stress is applied here. But if they are like in nature, that is both tensile or both compressive, we have to go for sigma 1 divided by 2. In plane maximum shear stress, this is another term for just asking maximum shear stress, that is in the particular plane the maximum shear stress is calculated as sigma 1 minus sigma 2 by 2. Okay, here they have asked the magnitude of maximum shear stress, just maximum shear stress. So it is sufficient to calculate sigma 1 minus sigma 2 by 2, which is 100 minus 40, 60 divided by 2, 30. The reason for this question selection is there is a possibility of thinking that sigma 1 is maximum, so 100 divided by 2, both are like in nature, so 100 divided by 2 will be 50. We will be choosing B, but they have asked just magnitude of maximum shear stress. If they have asked absolute maximum shear stress or tau max at a given point, this will be the right one. A solid circular shaft of diameter d is subjected to a combined bending moment M and torque T. The material property to be used for designing the shaft using the relation 16 by pi d cube root of m squared plus t squared. This particular relation is possible through maximum shear stress theory, that is a theory of failure. Here they have given options as ultimate tensile strength, tensile yield strength, torsional yield strength, and endurance strength. This is a 2009 1 mark question. Okay. In case of combined bending moment and twisting moment, generally when there is a bending moment, you will be having a tensile or compressive stress in a particular direction, and in the perpendicular direction there will be zero stress. That is, either it will be bending in sigma x or sigma y, that is in x axis or y axis. So one of the axes will be 0. In such a case only this equation is possible. That is, this equation is applicable where sigma x or sigma y, either of one is 0. Okay. Here according to MSST, the equivalent twisting moment is calculated using the formula root of m squared plus t squared, the bending moment squared plus twisting moment squared. Equivalent twisting moment is calculated using the formula pi by 16 d cube tau per, which is developed using the pure torsion condition. Okay, tau per is the permissible shear stress. So tau per can be written as torsional yield strength divided by factor of safety. So 16 by pi d cube goes here. This is the actual relation developed through MSST, that is maximum shear stress theory. So the strength which comes into play is the torsional yield strength. So the answer for this particular question is torsional yield strength. The state of plane stress at a point is given by sigma x is equal to 200 megapascal, sigma y is equal to 100 megapascal, and tau xy is equal to 100 megapascal. The maximum shear stress in megapascal is, they have asked the maximum shear stress. Okay, it is a 2010 1 mark and the values have been given as options. Okay, first the general formula to be studied to be used for calculating the principal stresses is this. Here the requirements are the normal stress in x direction and the normal stress in y direction, along with the shear stress on the x face in y direction, tau xy. That is, this is possible only for biaxial stress condition, that is two-dimensional state of stress condition. Okay, here sigma 1 and sigma 2 are differentiated by this plus or minus sign. For sigma 1 you will be adding these two, for sigma 2 you will be subtracting these two. Okay, as we know that tau max is equal to sigma 1 minus sigma 2 by 2, that is the maximum shear stress is this formula. Okay, upon simplifying, that is by substituting this formula here, we will be getting tau max in the form of sigma x, sigma y and tau xy they have given. This is a direct formula. But this, if you calculate by this way, you have to find sigma 1, sigma 2 separately and then you have to substitute. Instead of that, this is a simple formula which can be remembered easily. Here, instead of sigma x 200 megapascal is being substituted, sigma y 100 megapascal and tau xy is 100 megapascal, and the answer comes out to be 111.8. Match the following criteria of material failure under biaxial stresses sigma 1 and sigma 2 and yield stress sigma y with their corresponding graphic representations. These are called safe boundaries. That is, within this boundary, if the value comes, that is the stresses acting on a component comes out, then the material, that is the component, is safe. Similarly, here within this and here within this. Okay, first let us know the different shapes of safe boundaries for different theories. Okay, for maximum principal stress theory developed by Rankine, also known as Rankine's theory, sometimes as MPST, it is a square. So you may guess that maximum principal stress theory is also called as maximum normal stress criterion, because principal stresses are always normal. So maximum normal stress criterion. So P corresponds to M. Okay, then maximum shear stress theory developed by Govt and Tresca, sometimes called as Govt's theory. It is a hexagon. The safe boundary is a hexagon. For maximum distortion energy theory or maximum shear strain energy theory developed by von Mises, it is an ellipse. And for total strain energy theory developed by Haig, it is an ellipse. And for maximum principal strain theory developed by Saint Venant, it is a rhombus. Okay, from this you can understand that for maximum normal stress criterion it is M, and for maximum distortion energy criterion it is an ellipse, and for maximum shear stress criterion it is a hexagon. So RL. Here you can see PM, QN and RL. These are all theories of failure under biaxial states, or sometimes used under triaxial states also. Here we are seeing the safe boundaries for biaxial states only, that is sigma 1 and sigma 2. All these are derived for biaxial states only. The homogeneous state of stress for a metal part undergoing plastic deformation is, they have given the general state of stress at a point, that is 10, 5, 0, 5, 20, 0, 0, 0, minus 10. We have seen this as a stress tensor. So sigma x is 10, sigma y is 20 and sigma z is minus 10. This is tau xy, which comes out to be 5, and the other shear stresses are 0, where the stress component values are in megapascal using von Mises. Von Mises refers to maximum distortion energy theory, MDET, yield criterion. The value of estimated shear yield stress, they have asked the shear yield stress in megapascal. Okay, since they have given sigma x, sigma y, sigma z and tau xy, we have to calculate the principal stresses first. Initially, we have given the third principal stress because there is no shear stress in sigma z direction. So this comes out to be sigma 3. Whereas sigma 1 and 2 are calculated using this 10, 20 and 5. 5 is being substituted for tau xy 20 is being substituted for sigma y, and 10 is being substituted for sigma x. From the already known formula, we will be calculating the sigma 1, sigma 2, both principal stresses. That is by adding and another one by subtracting. After getting the sigma 1, sigma 2 and sigma 3, which is minus 10, this is the Von Mises theory criterion for failure. Sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square must be lesser than or equal to 2 times of the yield strength in tension. But according to Von Mises criteria, yield strength in tension and shear yield stress is related as follows. Tau ys is equal to sigma yt by root 3. After computing the sigma yt, this is being used and tau ys calculated, which comes out to be 16.07. This is actually a three-dimensional state of stress criterion. This will be reduced for a biaxial state, but here they have given a three-dimensional stress tensor. So this is the actual procedure to solve this question. A metallic rod of 500 mm length and 50 mm diameter, when subjected to a tensile force of 100 kN at the ends, experiences an increase in its length by 0.5 mm and a reduction in its diameter by 0.015 mm. The Poisson's ratio of the rod material is. It is a 2014 one more question belonging to set 1. Okay. We know that Poisson's ratio is calculated using the formula minus of lateral strain divided by longitudinal strain. Okay, what are lateral strains and longitudinal strain? Longitudinal strain is the strain happening in the direction of load acting. Here there is a tensile force acting along the length. So the change in length, that is increase in length 0.5 mm is the longitudinal strain, whereas the lateral strain is the perpendicular one to longitudinal strain, which is its change in diameter, which is 0.015 minus 0.015 mm. So just by substituting the change in diameter divided by diameter and change in length divided by original length, note that for lateral strain it is reduction. So minus 0.015 divided by the 50 mm diameter. Similarly, for 500 mm length, that is 0.5. This is positive because increase. So 0.5 divided by 500, you will get lateral strain and longitudinal strain. Just substituting here, you will be getting the answer as 0.3. A steel cube with all faces free to deform has Young's modulus E, Poisson's ratio V, and coefficient of thermal expansion alpha. Generally for Poisson's ratio, they will be using mu, but here they have given us V. Okay, the pressure, hydrostatic stress. Generally, pressure is a hydrostatic stress developed within the cube when it is subjected to a uniform increase in temperature. Del T is given by. Here they are stating about thermal expansion. First, we have to determine the condition in which thermal expansion is being done. And they have given the options here. And this is a 2014 one mark question being asked in set 2. Okay, they have stated all phases free to deform, which means this particular condition comes under free expansion. So for free expansion, stress induced is always 0. Thus, the internal pressure, that is the hydrostatic stress, comes out to be 0. But there will be thermal strain in all three directions, which is alpha del T. So the volumetric strain will be 3 alpha del T. But the stress induced will be 0. If it is restricted in a particular direction, that is in x direction or in y direction or in z direction, then there will be stress which will be equal to alpha del T into E, alpha del T E, which we have studied earlier. Okay, so according to the question, it is a free expansion question and it is free to expand. So the pressure comes out to be 0. So the answer is 0.